Hello, hope everyone is doing well. I wanted to discuss some ideas involving nanotechnology that we may or may not see in the future. Remember, it's from the perspective of a first year engineer student, so please keep that in mind. Some of this might be very basic. Let's start off with what is engineering? Um, so basically, people have problems, and engineers are working hard to solve those problems using technology through various industries, from utilities like lights and water to helping to maintain and create nearly everything around us. Anything, everything that isn't 100% natural, an engineer has had a place in improving it. From ancient times, the pyramids of Egypt, to cell phones, the ones we use today, and even the food we eat, an engineer had to design something in it. The upkeep of everything in our society relies on the work of engineers behind the scenes to keep it all together. The profession is very pragmatic, meaning they deal with issues in a realistic way, considering what's possible and what isn't. Engineering is creative problem solving, using every tool available, even creating new tools. There are limits to what people can do, and this makes the tools we use a little dangerous. We all know safety is always a concern that is factored into designing everything around us. A couple of months ago, you know, I had a thought that it would be easy to hold on to a plate of metal while I made a hole in it with my drill press, and it was not easy. Actually, made a huge mess. Um, a lot of people don't think about that, and things like this have to be considered when designing anything. There are financial constraints that have to be carefully considered too. Engineering is really a mix of business and technology, unlike scientists or physicists who are purely exploring and documenting novel discoveries. You know, gold is a great conductor, but if we tried outfitting an entire house with gold wiring, then we would quickly start questioning the homeowner's state of mind. Since we all know that copper wiring works just fine in this situation, a big part of the design process involves resources, cost specifically. Material needs to be bought and people need to get paid. Not a lot of people can work for free. What engineers have to do is work with limited resources and limited budgets, and the benefits have to outweigh the costs. Otherwise, there won't be much work next week. While as engineers design around some major constraints, there are still new and exciting technologies just making it out of the lab and into the consumer market. Like, for example, the people over at Metalbase uh, is putting together a desktop metal printer, something under $10,000 that prints metal powder and makes metal prototypes, basically. And they're doing it for 10,000, which is a lot less than the industry standard 3D printer that can cost upwards of 250,000, a couple $1 million. A lot of work is being done to improve materials, and innovations are happening every day. I'm pretty sure we're close to a fusion reactor, which is basically the holy grail of clean energy. The last update I heard was that a physical grid-scale nuclear fusion power plant is being built somewhere in Virginia. They managed to maintain a stable plasma for over 22 minutes. And yeah, that's actually pretty good with net positive energy production. But, compared to a stable 3-year reaction from a fissile material load, which is what we use today, that still doesn't quite cut it. We're getting there though. Uh, the materials containing the reaction are pretty exotic and under pretty extreme conditions. Similar to the sun extreme, advancements in materials will help solve these problems, hopefully. Like the advancements in nanotechnology, any material advancements seen at this level will send ripple effects up the chain of what's possible with design. This is where I wanted to focus, even though the other topics are massively interesting. Um, what is nanotechnology? Uh, Simply put, it's just technology that's at a certain scale. At the nanoscale, nano meaning 1 billionth, 1 times 10 to the negative ninth. Any technology involving nanometer structures are nanotechnology. About less than 100 nanometers, the equivalent, considering the sizes, just to get an idea, would be like us compared to the sun, as a nanomaterial is to us. Objects in this size scale have really interesting properties that are different from anything at the macro level. These properties can be very useful when incorporating into new designs. But to begin understanding these new materials, we have to understand what's going on with the properties of these structures. Since they're only a few atoms large, even seeing them requires special tooling. Tools we have is the scanning tunneling microscope. It's a device that is very sensitive to changes on the z-plane, up and down, while scanning over the x and y plane using forces of electron tunneling between an atomic tip and the scanner and the object being scanned. This data is recorded and organized as an image. Other ways we can look at things happening at this scale, but let's just look at two more. Also have a scanning electron microscope that projects images using a series of electron lenses to focus a predictable beam onto a surface objective while scanning the electron beam and using sensors to capture the reflected electrons and turn that into an image. This works on thicker materials and shows a lot of information. We also have the transmission electron microscope, which focuses a beam of electrons using electron lenses onto an objective that's being scanned. This objective, the material is only a few nanometers thick because the electron beam has to transmit through it, and this causes an image to be imprinted onto the electron beam. This beam is then projected and magnified using even more lenses that are then recorded by a sensor and turned into an image. We are moving towards understanding the world of different materials at the nanoscale, and we've actually come a long way. There's one particular material that is well documented and is actually already in production. Graphene. Back in 2004, we first created graphene, um, although it's been known to theoretically exist way back in 1947 by physicists. It's a single layer of carbon atoms arranged in a honeycomb structure, kind of like a sheet, kind of like a sheet. It's known to be a two-dimensional nanostructure because it has certain constraints within two axes, so an x and y axes. The material is known for its unusual properties, like high tensile strength along those axes, high electrical conductivity, and being completely transparent. The material is currently being researched for its use in next generation semiconductors, electronics, batteries, and composites, all for its novel qualities. It has potential for applications in NEMS devices such as pressure sensors and resonators, and throughout biological sensors for its sensitivity to small electrical changes. But, as you know, while it's an interesting material, it's not all great. The physical material is pretty dangerous, causing lung irritation and mesothelioma, along with a host of other issues in the body. It's a lot like the wonder material asbestos. So it's probably not going to the consumer market as a coating or additive anytime soon. This is a similar story with many types of nanoparticles. But besides graphene, there are a ton of other nanostructured materials that are available to us, like quantum dots, whose physical properties allow for adjusting their band gap and precisely tune what light they emit just by changing their size. This property is due to the qualities of their size at the nanoscale. So they have what's basically a virtual band gap around them that can absorb photonic energy and then re-emit, reflect, and do a bunch of other things with photonic energy. These are used in diode lasers and displays, even in medicine. There are a lot of other types of nanostructures that exist, like fibers, tubes, plates, even 3D nanostructures, each with their own characteristics and possibilities. It's good to know what's available. We're looking at new methods of creating these nanostructures. One interesting thing I found was following the nanostructures that already exist in nature, where organic life creates these structures en masse. DNA, in theory, could be modified to do our bidding at creating nanomaterials. One way they're trying to do it is by genetically engineering these things called bacteriophages, which are like a virus with DNA. And these can be engineered to be a biological tool by targeting specific mutations in them. These mutations kick off the production of specific structures in them, and then through the phage reproduction process of injecting their genetic material into a bacteria, and they could set up a bacterial environment. They could be used to create a bunch of nanomaterials all at the same time. I wanted to explore a specific area of development involving communication that looks like there's big potential in optical computing, which is just like regular electronic computing, but with photons instead of electrons. Here I have a picture from IBM that you can see in orange, copper data bars, and optical waveguides, the blue lines there, with this structure here grown in the middle, grown epitaxially, that does something important I'm not 100% clear on. If you think of the difference between data transferred through a regular cable and a fiber optic cable, fiber optic is used throughout high bandwidth applications like server management, ISP distribution networks, stuff like that. The optical photonic communication channels are much more efficient because they can utilize the physics of photons rather than electron propagation. Because photons are massless, uh, plus they're moving at the speed of light and also have some interesting qualities to them. Like, for example, they can be multiplexed, sending multiple uh, different wavelengths through a single channel, and then demultiplexed at the other side using a spectrometer to send much more energy, much more data all at once. We already have a good understanding for the development process for processors, including development kits, maps, various circuits and their functions. Manufacturing is done through multi-stage photolithography process, metal deposition, etc. Um, so creating photonic components and utilizing existing design processes uh, should be possible, especially with our current understanding of nanostructured photonic materials that can sort of move, guide, bend, diffract, diffuse light in all sorts of different ways. Many companies like Intel, AMD, even the US military are putting billions into the development of photonic processors to integrate them into everything from AI systems to autonomous vehicles. As for the future of engineering, I'm pretty sure recent interest in optical processors from big names means that there's plenty of room to find solutions for novel nanophotonic structures, especially ones that are possible using existing manufacturing techniques, photolithography, silicon manufacturing. In silicon optics is a big thing there. Um, a lot of this optimism is coming from physicists and engineers, not just investors, even though they're clearly very optimistic about it. Um, and Here we have one company, Light Matter, which has a working photonic chip. So, I've been waiting to say it, but the future is looking bright for this industry, uh, especially for nanophotonic structures, and silicon photonics. That's more than all my time, so thanks for watching.